So what about the other common twin plane in hexagonals, which is the 1/1/2? So here I've made a model where I've got a 1/1/2 plane shown here. In fact, I've got two 1/1/2 planes glued together. So the green crosses mark one plane, and then the one below it is another plane. So basically I have two planes stuck together, and that's the only way I could do it, so I could keep the planes together. But when they're mounted in a crystal, there's my 1/2 plane, and there's my basal plane. And when I can shear quite easily with one partial, and the partial being a 6/2 of R23. Now what I want to do is then shift this top layer here, another 1/23, to simulate the twinning operation. In fact, I can't because they're glued together. So what I have to do is take these end parts and show you what would happen next. So there's my basal plane. There's my basal plane, and this is the end of my 1/2 plane, and I've just basically disconnected these atoms from the rest just to illustrate this. So what happens is, given that my basal plane is parallel to my surface here, I'm now going to shear them using the 6/2 of R23 shear, which is what happens for twinning on a 1/2 plane. I'll do that shear now, one after the other, if I can hold these things together. There. And now you'll notice that there's the basal plane. So basically my second undistorted plane, the first undistorted plane is the 1/2 plane, but my second undistorted plane is the basal plane. So there's my basal plane. I shear and I shift my basal plane now up to an angle which is roughly 85 degrees to the base here. When I say that the first plane is undistorted, 1/2, as with most twinning operations, there has to be a little bit of shuffling going on. Even though you get the first major shear, there has to be some shuffling going on after the shear, which is typical of many shearing operations, because the atoms can't just simply shear back into the perfect lattice site.